Hello everybody, we are back to our class again. So let us bit recapitulate about what we are doing in our previous classes. So we started with some real life examples of plasma application, so that you find what the course content is going to do with the applications. Then we started with the Saha ionization equation. We told that what is the importance of that, and we applied that to argon plasma system, a monatomic systems. And what we have seen there, if we go, that partition function was playing a very important role, and we just explained how the partition functions can be calculated. Actually, you have learned all these things in your BSc course, but the thing is that you read about this and you knew that there are some formulas by which we can find out the partition functions. Like partition function is just sum over the states. Uh, but when you go for actual calculations, you need to know so many levels, so many transition probabilities, and this degeneracies for each and every your energy level, and that may go beyond say 400 in numbers, which are actively take part in which actively takes part in your this transitions and emissions and excitations. So finding this partition function was not an easy one, but anyway, modern days technology has made it much simpler. The advent of computer, we can do a huge amount of data handling at a given time. So it is not a problem, and actually you just believe that I have done all these calculations on my own, and I know that it is a very much tractable kind of thing. So now you have already come to know that how to find the compositions of argon plasma. But then why we are interested in knowing the number densities or different species that is generated at a particular temperature? This is because these are the agents who actually takes part in the reactions, high temperature reactions. Just one example I will give you. You know, in modern days, zero carbon emission is very much talked about. Now, in that, people earlier used to do reduction using carbon, so that they used to produce CO2. Uh, but nowadays, people don't want to produce carbon dioxide, so they don't want to use carbon. So what they want to do, they want to reduce say metal oxides using hydrogen, so that metal oxides become metal and H2 just get converted into H2O. And H2O, you know, this water and is very benign kind of thing, and you are really not producing any CO2, the greenhouse gas, due to the reduction. So that is a very attractive way. But when you use this molecular hydrogen, the reduction process is very slow, and it is not at all attractive. The moment you go excite them, like excited H2 molecule or atomic hydrogen or ionized hydrogen, then the reaction become very vigorous, and that reduction process is really worth. So that is the way. So at what temperature, what kind of ionization, whether the molecule will break or not, knowing is very much important for going to a particular process. So that is what about the this thing, what you call this monatomic gases. But most of the time we need to deal, rather many of the times we need to deal with molecular gases. Then what do we do? Whether the complexity increases or it remains at the same level. Just I will give you one example. I have actually handled much more complex, many molecular gases, atomic, monatomic gases together. But I will just give you one example of say oxygen. These gases are used in oxygen cutting torches, and I will just give an example how to handle these molecular gases. And then once you know the composition, then what directly you can get the thermodynamic properties and the transport properties. While thermodynamic properties, all the machinery, all the mathematical machinery you basically know from your statistical mechanics or thermodynamics classes, but how to actually apply them to real problem like this one what I am going to talk to, you will learn from this. Then regarding the transport properties, this is not that simple. You need to understand how the collision kinetics among the particles that is happening, and you are handling with plasma. So what will have, you have a collection of these positive and negative charge particles, and collisions what we used to know like collision between two marbles or two billiard balls, it is not exactly like that. In plasma, because of the long range coulombic interaction, they don't need to physically touch, still they can collide. So finding the collision cross section among different constituents of the plasma, it is very much important. So I'll just tell you the route to how to find that out, because this is very much necessary, and I have seen in my long experience that student, even they are passing their master's degree, but they really don't know how to find out the transport properties for any common gases. So this is very much important to know, and I am getting this opportunity starting from the ionization equation. I'll find the composition, and then how to reach to that thermodynamic transport properties. I'll give you this example of molecular gases, and then I'll finish the this part actually, and go to the next class. So this is what the example for nitrogen oxygen plasma. For example, here you see that here what we are handling, nitrogen and oxygen together. So this is basically mimicking the case of atmospheric air mostly. There are other components. If you remove them, then N2 and O2 mostly constitutes the atmospheric air. So here what we have done here, the species that we are considering, O2, the molecular oxygen, then O2 plus, the molecular ion, then O2 minus, again negative ion, then it is atomized, and you see that O minus also we are considering, and O plus, the first ionized, second ionized, O plus plus, and then O triple plus, third ionized state. Similarly for nitrogen, we are considering all these things, N2 and then N2 plus, N plus, and N double plus and triple plus. And you will wonder why O2 minus we have taken but N2 minus we are not taking. So these are all depending on actual situation, where whether it happens or not. Even O minus, this is very rare possibilities, but still we have included over here. Now O plus is very much possible, O is very much possible. Now you see here, here one thing that we are considering reaction between this nitrogen and oxygen as well. So they are forming NO. So not only we are considering the pure oxygen species or pure nitrogen species, we are, in this example, we are considering the reaction among them, and that is forming NO, and NO is getting ionized, the molecular ion NO plus. That also we are considering, and we are considering atomic oxygen, atomic nitrogen, and of course electron that is coming out from all these ionized species. Now you see that it is mathematical this convention that we number each of these species by a number. Like species number 1 is O2, and species number 17 is electron. Now we have marked their masses, and the number density is also by some parameters. We are using this. Then what we need to do, we have seen that we start everything with psi ionization equation, as I told you. But when you go for this non-equilibrium kind of situation, then you can derive the psi ionization equation from the Gibbs free energy minimization. So that I have just used here, and I have got the final result like this psi ionization equation. I can see the third column that is listing over there, and the rate constant what is on the right side, that has been listed on the fourth column. And for every actually ionization or dissociation, you need to supply some energy, and the amount of energy you can find from the literature. It is available, and I have just listed those things as I have obtained from the literature here. So similarly for nitrogen and for NO, you got all those things. And as I told you that this Saha-Henriksen equation itself may not be sufficient for solving these equations. You always get the number of unknowns, that is the number of species present in that ensemble, is more than the available equations. So auxiliary equations that you require is the total pressure, charge neutrality, and the ratio of N2 and O2 that you are mixing, whether it is in the your atmospheric ratio or you are creating your own ratio of N2 and O2. So depending on that concentration, so you will get additional equation for the ratio, and other two, charge neutrality and the total pressure together, that will complete the set and you will be able to solve these equations together. So I have solved this, and you see that the different species densities, as you increase the electron temperature, that goes like this. It is a pretty complex kind of thing, and you can see that N2 is being formed, NO and NO, everything is getting formed. And what we need to know, how they are varying with temperature. And this is not very much clear from this kind of plot, where we have done that your vertical axis is a log plot and horizontal axis is linear. So from this it is not very clear how the things are happening, but anyway we come to know why it is peaking and what kind of species are getting generated. And advantage of log plot is that you can show the results over a wide range of orders. You see that I have started with 10 to the power 10 and I am ending with 10 to the power 26 on the vertical axis. This is absolutely not possible in linear scale. So that is why actually we used to go for this log plot. But there is another way to find out how they are varying very nicely. You see that here we have plotted mole fraction. What is mole fraction? I already explained you that it is a concentration of certain species divided by the concentration of total species. So that will give you the mole fraction, and its value will never exceed 1, as you have seen over here. And you see that how they are varying here. In the upper left corner, you see that it is starting N2, and of course I have taken the rest of the part is O2, that is 0.2 is contributing, so it is starting from 0.8. So 80-20 ratio of N2 and O2. So it starts from 0.8 and then it remains like that. A certain time comes when the molecule dissociates and N starts forming, then N peaks, and then N goes for dissociation and N plus forms. Then N plus again get dissociated and N plus plus form. But here what is happening, in the total mole fraction, oxygen is also contributing. So you have to consider all the species that is getting generated in finding the mole fraction. So this is the kind of behavior that you get, and the feature is very clear. And when you go for non-equilibrium, like when you are saying that temperature of electrons is same as the temperature of heavy species, then the kind of feature that you get is on the upper left corner. The graph is there. But the moment you go for non-equilibrium, see 2, 3 and 4, the 2 is the bottom left one, and then upper right is the 3, and then bottom right is the 4. You can see that the number density pretty well depends on the kind of non-equilibrium that is reigning over the plasma. So non-equilibrium consideration is very much important, and that is basically the research of the day actually. Earlier equilibrium things many people have handled already, but non-equilibrium things, they are just emerging nowadays. Now I am showing you the equilibrium case, and here what we are finding, the transport properties, thermodynamic and transport properties. I have already shown you the recipe to find out the density, enthalpy and specific heat. They are pretty simple, and you see that there is not much ambiguity in this. Whatever I have calculated the solid line and what literature has given, they are the this dotted dots that I have collected from the literature, and they are pretty well matching. Actually, there is very little dispute about the thermodynamic properties. But the moment you go for the your transport properties, you see the bottom right corner, the figure. You see that what we have calculated is the your solid line. and this is the thermal conductivity. Now, when you compare that with those having in the literature, you see that the scatter is too much, not at the lower temperature side, but at the higher temperature side. And there are several peaks, of course, and why are these peaks? So that kind of thing, why they are there, if you want to understand, then you need to go to the deeper into the physics that is associated over there. Well, so what I mean to say that there are ambiguities when you go for calculation of the transport properties. Why this is so? This is mainly because the kind of data that you require is the collision cross section or collision integrals for collisions among different particles in the plasma medium. Now, the kind of interaction depends on the kind of particles interacting. Like if you go for this two charge particles, definitely the interaction will be Coulombic kind of thing. But when you go for neutral interaction, so there you may go for some polarizability model or something. You have to model that phenomena, and there the approximation get introduced. So when you are going for neutral interaction, neutral charge interaction, charge interaction, the type of interaction potential, they all together are varying actually, and exact potential through which they are interacting, there are certain doubts, and that is basically causing the scatter in the data. But anyway, day by day the things are improving, and you can see that latest studies are basically giving the result what we are getting in this graph. Now, this is one interesting thing just I wanted to point you out. When you think of this thermal conductivity, for example, solids we have done in our school days, and you know that we never thought of there is only one conductivity, thermal conductivity is there. But when you go for plasma, you know that total thermal conductivity is consisting of three major parts. One is by the electrons. You see the dotted line which is going up, and then there is one for the heavy species which are heavier molecule other than the electrons that is there. And there is one very special that is called reaction thermal conductivity, reactive thermal conductivity. So this one originates mainly because when there is a dissociation is involved, when there is a fast ionization is involved. So this kind of your chemical reactions like dissociation, ionization, they contribute to this thermal conductivity. So they are called reactive thermal conductivity, and that is basically contributing to the peaks. So when you calculate the total thermal conductivity, you need to add up all these three actually. So this I have just introduced only to tell you what is actually the picture there. I am not going into very detail of these calculations because that will not be sufficient to discuss in this course. So if you are interested in detail, then you can of course go for these things. Hisfelder, there is one book where all the recipes for calculation of these thermodynamic properties are given there. Now, this is another thing, as I told you that finding the thermodynamic properties is a bit easier and there is less ambiguity, but when you go for this calculation of transport properties, and you need to understand the collision integrals and collision cross sections for that actually, and how they are finding, how they are found. So you start with some interaction potential for the interaction between these two particles. Then you calculate the deflection angle that I have given the formula. Then you get gas kinetic cross section from that deflection angle. And then you get the collision cross section and the collision integral. So they are defined exactly the way they are done there. And for charge and interaction, you can go through the recipes that I have given on the upper right corner. This is basically for Coulombic interaction. And here you can get the collision integrals in a very precise form as given there. And you can convert collision integral into collision cross sections using a formula that is on the lower right side. So why I am showing this slide? This is pretty complex things inside this, and a good amount of computational effort will be required if you want to find them out. But I am showing these slides just to give you an impression what is the route to find out this collision cross section and collision integral, without which it is never possible to find out the transport properties. Just to give you a route map how to find them out. So what essentially is there, if you want to calculate the cross section and collision integral, then what you have to do, you have to start with some interaction potential, the best one that you think that will be working there. Then you can go through these mathematical procedures to find the cross section and integral. And for charged particles, you can proceed through the same route, but there is one very precise and nice formula for getting those integrals. And cross section and integrals, they can be converted from one to other using the formula that has been given on the lower right corner. Now, as I told you that I will be giving you one example of nitrogen oxygen model as we started with. You see that we had 17 species as I started with, and each of these 17 species is interacting with each other, each of them actually. So 17 species are interacting with 17 species. So that O2O2 interaction will be there, O2O2 plus interaction, O2O interaction, O2O minus interaction. Like that actually each of them will interact with every other that is present inside the plasma. And I have used a color map. You see that charge integrals, they are marked in yellow. Electron neutral interaction, that has been marked in green. Similarly others. So this shows that inside the this system, N2O2 system, different species are generated in the plasma and all of them interacting with each other. And the type of interaction, they are different for different type of particles. So for each of them, you need to find out the right potential that should be applicable there, and you need to calculate all the collision cross sections and integrals. Once you are done, then you can calculate the thermal conductivity using the formula that has been given there. You are seeing that there are certain parameters like Q11, Q12, Q22, they are there in the formula. And these parameters, Q11 for example, or Q12 or Q22, they are actually related with the cross sections and integrals. And you can, precise expression, they are available as I told you in the book of Hispelder or their previous works by other researchers in the area. They have given precise formula how to find out this Q11 in terms of the collision integrals. So that can be used over here. Similarly, for these thermoconductor heavy particles, and that for the electrical conductivity for the plasma and viscosity, all these things are having some or other formula which are written in terms of this collision integrals and cross sections. When you evaluate this, you get the your transport properties. So just let me tell you, because I have done all this calculation, I know the issues. The problem is that here these formulas are many times coming in the form of ratio of determinants, and these determinants, you know, started with zeros, and sometimes you are handling of quantities of the order of 10 to the minus 200, 10 to the minus 300 kind of thing, and computer, the moment you give it to computer, that will straight away say that it is zero kind of thing. Now, when you are having two very small quantities, say 10 to the minus 200, and you are taking another quantity which is 10 to the minus 201, they are pretty small. But when you take a ratio of them, then it will become 10 to the minus 200 by 10 to the minus 201. It is simply 10, and that is not negligible. So you need to find a numerical recipe how to handle these very small numbers in a computer. So that is a bit of challenge, and there are ways to tackle them. So I am just telling the complexity that is involved in these computations. So that is all. Now similarly, there are diffusion coefficients which you will always require to find the transport properties, because whenever there is a gradient, one particle is moving into the another, there may be number gradient, there will be temperature gradient, and you know there is something called ambipolar effect in plasma. This is purely due to the charged particle behavior of the plasma. I will describe all this in detail, this ambipolar diffusion coefficient, in a later class. But here only I tell you that there are different diffusion coefficients involved in plasma, like binary diffusion coefficient, general ambipolar diffusion coefficient, general diffusion coefficient, then thermal diffusion coefficient, thermal ambipolar diffusion coefficient. So and they are different for different particles, like it will be quite different for electrons and ions. So all these parameters you need to know to find out the transport properties. And because of such complex dependencies and uncertainties in the exact potentials which they are interacting, the differences in the values of transport properties that arises. And these transport properties we require because they determine the thermal field which is being used by the processes, and the thermal field basically decides the species that is getting generated over the domain, and they are basically responsible for the specific process that is going to happen over there. So that is why it is very much important to know the transport properties very precisely, and researchers all over the world are trying to find out more and more accurate values, and we are also in that process. So I just show you here the sum of the transport properties that has been calculated here. The upper left one is the thermal diffusion coefficient of electrons, and the right one is electrical conductivity, upper right one, and then bottom left is the thermal conductivity of heavy particles, and the bottom right is the viscosity. So you see that the solid line that I have calculated, they are more or less matching with the data of others, but there is a pretty good scatter. But this was not the same, if you remember, in case of the thermodynamic properties. So that is how the properties goes on, and the thermodynamic and transport properties decides the velocity field, pressure, and your temperature field, and those in turn basically decides the efficacy of a process. So they are very much required to know, but the mechanism how to find it out usually not available in plasma books. So that's why I am emphasizing on this process when I came to the Saha ionization equation. So we get the number densities, you find out the thermodynamic properties, and you find out the transport properties. And how to do that, at least you know the route how to find them out. So after this, I'll basically move away from Saha ionization equation, because we now have understood a lot about this, how to find out the species that is getting generated in a plasma, and then what are the properties that will be there. So once we know the species that is getting generated, they will be either ions, double ions, electrons, or neutrals. Usually these are the things, but if you go for this metallic species, then they get very easily ionized because of their low ionization potential, and you may get triple ion and more than that actually. And sometimes this plasma having higher charge states are very attractive, because when you go for this ion acceleration like accelerators, if you are able to produce higher charge states, then what you will get actually, you will easily get more acceleration, because Q into E is the force and E is the electric field. For a given electric field, you will be able to get more acceleration in that case. Okay, so that is what I wanted to say in this class. I stop here, then meet you in the next class. Okay, thank you.